In the last lesson, we learned that if we wanted to find the area under a curve, we could find a bunch of rectangles and break that into a bunch of rectangles, and that would give us an approximation of the area. And if we had more rectangles, then we could find the area better. Well, let's look at something called a summation that will help us do this. So first, let's consider a little problem here, a problem that was given to a young mathematician named Carl Gauss by his teacher, who was trying to keep him busy because he was too smart. And he was sent to the back of the room to keep him busy. And his teacher said, "Hey, I need you to add up the numbers to 1 to 100, and that should take you a while. Come back when you're done." And a few minutes later, he came back. Not even a few minutes later, a few seconds later. And let's see if we can figure out how he added these up. So can you do this? Can you add up the numbers 1 to 100 pretty quickly? Maybe pause the video if you want to think of a creative way to do that. Well, what Gauss did, and what you may have done here, is if we take some numbers like 1 and 100 and add them up, we get 101. 101. If we take 2 and 99, we get 101. If we take 3 and 98, we add those up, we get 101. And if we keep adding all these pairs, we notice we get 101. So how many pairs will there be? Well, since we're pairing up from 1 to 100, there will be 50 pairs. So we have 101 times 50, which is 50, 5,050. And there's our answer. Pretty quick. So there's quick ways to add and there's slow ways to add. If we add these 1 plus 2 plus 3, well, that would take a while. But we can find some clever ways to do this quickly. So one tool we're going to use is something called sigma notation. So sigma notation looks like this. We're going to write this 1 to 100 sum like this. We're going to say this is the Greek letter sigma. And this tells us we're going to have a list of terms from 1 to 100. So 100 terms, and this defines the term here. So we're going to plug in 1. So I is what we call an index. And so the first term is defined by putting 1 into here. That's 1. And then our counter, this is like a counter, is going to go 1, 2, 3, 4, 5. Okay, so our counter becomes 2. And we'll plug 2 in there. And that gives us our next term. In the next term, we plug in 3 all the way up to 100, the last term, and there'll be 100, and we're going to add them all up. So sigma notation it works this way. So we have n terms. N is the number of terms. N is this upper number here. And those terms we'll call a sub 1, a sub 2, a sub 3, all the way up to a sub n. And each term is defined in some way. So we're going to take the number 1, we're going to plug it into wherever there's an I, and that will define our term. So I here is called the index of the summation. And AI, these AIs, A1, A2, A3, are called the ith term. And these are the upper and the lower bounds are these numbers 1 and 100 in this case. So 1 and n, sorry. 1 and n are the bounds. It's where we start and where we end. So let's see how it works. Let's look at some specific examples. And let's write these out and find their sums. So first we're going to plug in 1 here to get our first term. So we have 2 times 1. Then we'll plug in 2. Then we plug in 3 to get our third term. So we're always plugging these numbers into where there's an I. Then 2 times 4, and we're going to keep going until we hit 5. Plug in 1, plug in 2, 3, 4, and 5, and we stop there. And now we can compute these out. These are 2 plus 4 plus 6 plus 8 plus 10, and that comes out to be 2 and 8 is 10, and 10 and 10, which is 30. Okay? Well, we don't have to have I. We could have another letter like J. So if we plug in 1 to 4 into J here, we'll get something like this. 2 times 1 plus 1 plus 2 times 2 plus 1 plus 2 times 3 plus 1 plus 2 times 4 plus 1. All right? And so that comes out to be 3, 5, 7, 9. All right? And what does that add up to? Well, 3 and 7 is 10, 15, 24. What about, well, we can square. Same idea here. We don't have to start at 1. We could start at 3 or some other number. So we have 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared plus 8 squared. All right. 9, 16, 25, 36, 49, 64. Oh boy, this is going to test our adding here. Well, 9 and 16 is 25, and 25 is 50. Not so bad so far. 50 and 36, that's 86. 86, oh boy, 86 plus 50, that's would give us 136. Minus 1 is 135. And 199, I believe that is. All right. But the idea is we don't have to start at 1. Doesn't have to be I. Doesn't have to start at 1, but this gives us our counter. And every time we plug in one number and the next one and the next one, and that gives us a new term. Okay? Sometimes we will have expressions that have an n in them here like this. Okay? Now, notice there's no i's here. Okay? So if we had this expression here, the first term would look like this, 1 over n times n minus 1. That's the first term. The second term would look like this, 1 over n times n minus 1. The third term would look the same, and we'd do this a whole bunch of times. Well, how many times would we do this? Well, we do this n times. So this equals n times 1 over n times n minus 1. Well, what is n times 1 over n? N times 1 over n here is just 1. So this is equal to n minus 1. So we don't always even have to have numbers. Okay, we can now start to think about what it would be equal for any number in this case. Okay, and we'll often do this little dot, dot, dot because we can't write these out. We don't know how many there are. So we just have to kind of think about it theoretically, kind of. And last but not least, we have this expression here that's going to be an important one to us. In the last lesson, we talked about finding the area under a curve, and we broke it into a bunch of rectangles. And each of these rectangles had the same width, and the height was determined by the function. Well, that's what this expression means right here. So this delta x would be the width of each rectangle there, and assuming they're all the same here. So if we have a bunch of rectangles that are the same width, then this expression represents the f of the first x value, x1, times the width, delta x, plus f of the second x value times delta x, plus, and so on and so forth. So this is the area under a curve, all right? And we'll come back to that after we start to understand a little bit more about this sigma notation. Now, to help us to understand or to simplify some sigma notations here, we need to look at some certain patterns here. So we're going to start by looking at the sum of the first 100 even numbers. So the even numbers are 2, 4, 6, 8, 10, so on and so forth, of course. So if we add the first even number, well, that's just 2. If we add the first 2 even numbers, that's 6. The The first three even numbers, 2 plus 4 plus 6, that's 12, right? Yeah. If we add up the first four ones, that's 20. Add up the first five, that's 30, and so on and so forth. Okay? Well, now we're going to look for a pattern. If you want, you can pause this, and you can think about a pattern there. Let's see. Well, we notice this is 2 times 1. No, let's write that as 1 times 2. So we might ask ourselves this. We might ask ourselves, is there a constant difference here? That should be a 30 there. Nope, doesn't look like there's a constant difference. We're going up by 4, then 6, then 8. Not a constant difference there. Well, is there anything we can do to this number to get the sum? Well, 1 times 2 gives us 2. 2 times 3 gives us 6. 3 times 4 gives us 12. 4 times 5, 20. 5 times 6 is 30. Aha! I think we found something. So if we take the number, the times one more, we'll have our sum. So 100 times 101 is going to give us 101 or 10,100. So what is this formula we're looking for? This is n times n plus 1. And this, by the way, these are called oblong numbers. Or sometimes people call them rectangular numbers. So the way that the reason why we call them oblong or rectangular numbers is because we can, if we draw pictures, and the Greeks did this. When the Greeks looked at numbers, they thought of the numbers as pictures of squares or dots or rocks. Okay, and so if we have 1 times 2, 2 times 3, 3 times 4 looks like this. And each this number of dots can be made into a rectangle. So these are called oblong numbers or rectangular numbers. N times n plus 1. Okay, well, what about these numbers here? What if we add up the first 100 natural numbers? So we have 1, 2, 3, 4, 5, 6, so on and so forth. These are natural numbers. Okay, natural numbers are just counting numbers. Add the first one, you get 1. Add up the first 2, 1 plus 2. Add up the first 3, 1 plus 2 plus 3. We get 6. Add up the first 4, we get 10. Add up the first 5, we get 15. So when the Greeks thought of this, they said, okay, I'm going to take 1, and then we're going to add up 1 plus 2. Then we'll add up 1 plus 2 plus 3, that's 6. 1 plus 2 plus 3 plus 4, that's 10. 1 plus 2 plus 3 plus 4 plus 5, that's 15. Notice these make nice triangles. So these are called triangular numbers. And so what's the pattern here? If you want to pause, you can explore it for a second, see if you can find it. Well, there's a connection between the top one and the bottom one. Can you tell? 2 becomes 1, 6 to 3, 12 to 6, 20 to 10. Notice they're half. So it's half of that. So half of 10,100 would be 5,050. Notice that's the question we just did at the first part. What's the sum of the first 100 numbers? Counting numbers, that is. It's 5,050. So half of this gives us n times n plus 1 divided by 2. And those are the triangular numbers. Very important numbers in mathematics. So a couple more here. What about if we add up the odd numbers? So we add up the first 100 odd numbers. So that's 1, 3, 5, 7, 9, 11, so on and so forth. Well, if we take the first odd number, 1, and that's just 1. Now take the first 2, 1 plus 3, that gives us 4. So I'm going to take 1, and I'm going to add 3 to my little rock pile. That's 4. And then we add another one, add 5 to that, you get 9. So I'm going to add 5 numbers to my little rock pile. my 5 blue dots there. Now add up the next odd number. That would be 16. So I'm going to add 7 numbers to my rock pile here. 7 little red dots here. You see what's happening? What kind of numbers do we have? Well, they're square numbers. Every time I add an odd number, I get a square number. So this is 1 squared, 2 squared, 3 squared, 4 squared. 100 squared would be 100, 10,000. And we have n squared. Okay? Kind of a nice pattern. Well, what if we add the square numbers? So if we have the square numbers are 1, 4, 9, 16, 25, 36, we end up getting these numbers 1, 5, 14, 30, 55, so on and so forth. Well, this pattern is a little more complicated, and we're probably not. You can work on it if you want to pause and explore. Go right ahead, but we end up with a formula that looks like this. We have n times n plus 1. Well, that sounds familiar. Times 2n plus 1. Oh, that's different. Divided by 6. And this is one we want to get familiar with. It kind of looks like the triangular numbers with the n times n plus 1. We've got times this odd number and not divided by 2 or dividing by 6. So, and if we use that for 100, we get 100 times 101 times 2n, so that'd be 201. 2 times 100 plus 1 divided by 6. And that comes out to be 338,000. That is 350. All right. Well, so there's some useful formulas. All right. So now we'll use those formulas. Now, what does that mean to us? Well, this up here, this was the sum of the even numbers. So we can write that as the sum of I equals 1 to n of 2i. Even numbers are 2 times I. And if you work this out, you'll get 2, 4, 6, 8. All right. And so this is equal to n times n plus 1. And even more important, this is one that we'll want to memorize here. The sum of I equals 1 to n of I is n times n plus 1 divided by 2. This is the sum of I equals 1 to n of the odd numbers. Well, the odd numbers are 2n plus 1. Okay, not one that we'll necessarily need to memorize there. Useful to know. They add up to square numbers. And this is definitely one we'll want to know. The sum from I equals 1 to n of the square numbers, and that would be I squared. And that comes out to be this. So now if we have a sum, we can write this as an equation in terms of n there. All right? Two important ones there. We have the sum of I and the sum of I squared there. Two ones that we'll want to memorize. So now we can use these formulas and we can work with these sigma notations. And we don't have to necessarily write out the whole summations. So some things to remember here. Remember that sigma notation is just a shortcut for writing out a long string of terms. So we can do algebra with sigma notation without writing all those terms out. We might have hundreds and hundreds of terms, but we can do a lot of work with it without actually writing those out. So using the distribution and the associative properties, we could say this. The sum of k being just some constant, times some term. Well, this is just a bunch of terms added up that have a k in them. We can factor that out. All right? And so what that means is this. If we have something like the sum of, let's say, I equals 1 to 4 of, let's say 5 times I. Well, that's just 5 times 1 plus 5 times 2 plus 5 times 3 plus 5 times 4. Well, we can factor out that 5 because 5's in each of them there. And this is just 5 times 1 plus 2 plus 3 plus 4. And that is just 5 times the sum of I equals 1 to 4 of I. All right? So notice the 5 that was on the inside there just gets pulled out because it's really just factoring. Okay? Distribution in reverse. That's all this rule is saying. All right? Also, we could say this. If we have a sum of two things being added together, two terms, we can break that up. We can take these two terms and break it up into two summations from 1 to n, okay, or whatever the bounds are there, okay. So, for example, if we have the sum, let's say again from 1 to 4, of, let's say, I plus 7. Well, let's write that out. We got 1 plus 7 plus 2 plus 7 plus 3 plus 7 plus 4 plus 7. Well, if we rearrange that, that's just 1 plus 2 plus 3 plus 4 plus 7 plus 7 plus 7 plus 7. And that can be written as the sum of I equals 1 to 4. Now this first part here, that's just the I numbers. Okay, so that can be written like this. And plus, let's see, this part right here can be written like this. The sum of I equals 1 to 4 of 7. Okay, this sigma notation here, notice there's no I in here. Each term is 7. There's 4 terms, 1, 2, 3, 4, and each one is 7. That's what this is, 7, 7, 7, 7. Okay, we'll talk about that shortcut there in a second. But anyways, the point with this part, this rule, is that what we started with was I plus 7 in one summation, and we can break that into two parts here. Okay? And that's nice because then we can deal with each part separately. Now, you might notice this. Take a look. This is just 7 being added 4 times. And how would you figure that out pretty quickly? Well, that's just 4 times 7. Okay? And, how do we figure this out quickly? Well, we had a formula for this, right? We just did it on the previous page. So we have n times n plus 1 over 2. This is n. So we have n, which is 4, times n plus 1, 4 plus 1, all over 2. So now we can compute these two things separately. And so 4 times 5 divided by 2, that gives us, that gives us 10, right? And 4 times 7, that's 28. And so this is 38, right? So we now can see a couple things. We can break these summations up, and then we have some shortcuts. Once we realize what's actually going on, we have those formulas for the sum of I being n times n plus 1 over 2, or if it's just a constant, we have n times a constant. And that brings us to these summation formulas here. Okay, if we have the sum of some constant c, like the 7 we just saw, then that'll just be n, whatever number's up here, times the 7, or c. If we have the sum of I Now notice I is the counter. That's the sum of the natural numbers. That'll give us n times n plus 1 over 2. So whatever number this is, plug it in. If we have the sum of I squared, we saw that previously, n times n plus 1 times 2n plus 1 all over 6. And I cubed, we won't see this very often, but it comes out to be n squared times n plus 1 squared over 4. You won't necessarily need to memorize this one, but these other three we want to have down. So let's do some algebra here with our summation. So we have this expression, the sum from 1 to n of I plus 1 over n squared. Now, n is a constant. In a few minutes, we're going to plug in 10, 100, 1,000, whatever number you want. But right now, let's just leave it alone. All right? So let's just do some algebra with it, see how this works. So we have the sum of I equals 1 to n of I plus 1 over n squared. Now, remember that n is a constant. Another way that we can write this is I equals 1 to n of 1 over n squared times I plus 1. All right? Now, we know that when we have a constant, we found this out up above here, this rule right here, when we have a constant times an expression, that constant can get pulled out. Now, I know n looks like a variable because it's a letter, but it's actually it's not the variable I. It's not part of the counter. All right, so it's not changing in this expression here. So we're going to go ahead and pull that out. And we get 1 over n squared. I equals 1 to n of I plus 1. Now, we have another rule that says, if I got the sum of these two things being added, we can split them up. All right, well, let's go ahead and we've got the 1 over n squared that's got to hang out. We're going to need some big parentheses here. And we're going to break this into two summations. I equals 1 to n of I plus another sum of I equals 1 to n of 1. There you have it. Okay? And now we can clean this up a little bit further. Okay? So this, still 1 over n squared, times, well, we know that this little thing here is going to be n times n plus 1 all over 2. And this is going to be n times 1, which is n. Oh boy. All right, we're getting somewhere. And now, let's go and distribute this back out. So if we distribute this out here, we're going to have n over n plus 1, or n times n plus 1, I should say, over n squared times 2, okay, plus n over n squared. And last but not least, let's go and clean that up a little bit there, and we can have this as, cancel one of those with one of those, and we'll have n plus 1 over 2n, and we have 1 over n. And in fact, let's go ahead and let's make this as 1. Let's multiply by 2 on top and 2 on bottom to get a common denominator. And we have n plus 1 plus 2 all over 2n. And that's just n plus 3 over 2n. All right. Well, that's not too complicated. So this whole thing is n plus 3 over 2n. So the sum of I equals 1 to n is n plus 3 over 2n. So if we have if n equals 10, then this becomes 10 plus 3 over 2 times 10, which is 13 over 20. If n equals 100, well, this is 100 plus 3 over 2 times 100, 103. And we can crank this up to 1,000. And we get 1,003 over 200, nope, 2,000. Okay, if n equals one more, 10,000. Well, this is 10,003 over 2,000. Well, what? One too many zeros there. Nope, it was 20,000 because we're doing 10,000. Okay. Well, in the end, what is this really going to? Well, this 3 doesn't really matter. This is basically 10,000 over 2,000. So this is approximately 1/2. Right? So we can kind of see as we look into limits, if we can evaluate this expression, and then we can think about what's happening as it gets larger. Okay, so we can do the algebra first. So, well, there you have it. All right, that's how you simplify those things there. So the final step is to take this back to area. So we'll see next how that works.